Hello. So, we've got a knapsack and a box. Can we use artificial intelligence to fill our backpack? So, first thing we need to do is to open my GitHub, which I've got here, and you will find it as the same address, github.com/fpert041, and we go into DFO, my repo DFO. You clone or download this if you haven't got it already, and then we quickly, ah, oh my god, look at that face. Anyway, so what we do next is we open Xcode. Once you download it, of course, I've already got it. You basically get started with not another playground. Actually, we want a new new Xcode project, command line, because we want C++. If you're not on a Mac and you don't have Xcode, you will basically want to do the same thing, and we'll call it knapsack. How are we gonna fill a knapsack with? As you can see, I've already made quite a few of them, and but we'll start from scratch. So we'll create a new one, but obviously I need to change name because I've already got another one. So let's do knapsack new, and let's put it anywhere you want, really. Done. So next thing we have to do, that's me again frozen. Next thing we need to do is to find wherever you downloaded your DFO, which in my case is here. Very quickly found it. Now this is the folder that you download, okay? And inside you find these two things. So what you want to do is to drag this folder into this, and you want to make sure that basically all the CPP files are linked to the project and the header file is there. Then you go into main and you include the header file, and what you do is to type this DFO dfo.hpp. This should work. So we go and compile it, we build it. Can't find it. Right. Why can't you find it? Is it 4 levels? Possibly. Let's try again. And it finds it. Right, so now we're ready to rock and roll with our new challenge. Let's fit a knapsack with objects using artificial intelligence, in particular swarm intelligence. First thing we need to do is to clearly define the problem. The problem we've got is that picture you have a knapsack or a rucksack, right? And you want to fit it with objects. Each object has a profit, a value, so you want to have as much value as possible, but they also have a weight, and there is only up to a certain much capacity that the bag can contain. So we want to find the best possible combination of objects to fill this knapsack so that we've got the maximum value of filling all the space possible. Now to do this, we're gonna use DFO, my lovely artificial intelligence swarm algorithm, and we'll use some object-oriented procedures. So what I'm gonna do to keep things neat, we're gonna create a class and we're gonna call it nap. It's going to go there. We don't really, we're not really too fussy about it. So in main, we want to include now nap.hpp, which will link our file. And let's say that what we want to do is that we've got a class that we'll call nap, and we'll basically have for sure a function to set up. So that's public, by the way. We'll definitely have a setup function, where we create basically the settings of the algorithm, because that's how DFO works. We need to set it up. Then we'll need a run function that updates the algorithm basically all the time. And this should be the structure. I mean, yeah, that's all we need. And in CPP, obviously, you want to define it. So we've got void nap setup and nap dot run column, sorry, not dot. And then in main, what we want to do is that we get rid of this. We call it nap k, and now we've got our nap object, which is obviously empty. Now what we're going to do, first of all, we want to have nap to contain an instance of a DFO, so we'll import it, include DFO, and as a matter of fact, let's see if this works. Yes, it does. So we are going to have DFO, just standard DFO implementation, and let's see if it works. Yes. Now, where are we gonna get our data to test and work with? I've got this website here that I'll put the link in the description, but basically has some data for the knapsack problem. That is exactly what I've defined before. Now I've already made some notes here. Basically all this stuff is the data from that website. There are several examples and I put them into arrays, and this way we know exactly what we're going to find, what we're going to have, and we can test it with basically the same data, sort of hypothetical knapsacks, hypothetical weights, and profits, and so forth. Now what we need is we need to include standard vector and array. Very quickly, because that's what we're going to use here. Now this should work. Brilliant. Now we want to have a way of passing this stuff in, and to do that we might want to change the constructor of this, and we might want to pass this stuff in equals nap, and we may want to have a nap capacity just one, just the first element, for example, and we may want to have the weights, again just the first example, and we want to have the profits, because as you can see there are vectors or arrays of vectors, and vectors like the vectors of vectors to the structures basically. So the first one is just the capacity, so there is one knapsack per problem, so just one number, and the weights are obviously sets. Each problem has a different set, so they are arrays of vectors, and it's complaining because we haven't defined the constructor this way, but it doesn't matter because we can put a remedy to this, and this define the knapsack constructor as such. So we need an int, okay, and that's gonna be the knapsack capacity, and we need a vector of int that's going to have the weights, and we want a vector of profits, the vector of int called profits. And we'll have to define what happens to these guys. So let's just go quickly here and define nut. And now we've got a constructor, and we'll finally have variables nut capacity. We'll have basically the same variables, okay, and the difference is that we want to pass in those values, so I'm going to just go in, and copy this, go back here, here for a second, and then that's what we're gonna do. We're gonna define them, we're gonna take them in from outside when we pass them in, and there we go, just very quickly. And obviously this line has to be inside of the constructor. Now we should be up and running. We're not, something is happening somewhere here. Call to implicitly deleted constructor. Well, actually you should be alright. Why aren't you? Okay. We want to take in an int. Oh well, me silly. That's what you were complaining about, right? Yes. Great. So now we're passing in the first set, and what we want to do is we want to obviously set it up, and we want to run it. Now, nothing is going to happen if I run this program because the two methods are empty, but let's just run it for the sake of argument. Done. That was it. As I said, there's nothing happening because nothing is going on here. But what we're going to do now is we're going to just quickly fill it in. So we've got our data, and we want to fill it in with stuff. Now let's quickly have a look at DFO. First of all, we want maybe to have a variable that's gonna store the number of objects. That's gonna make our life easier. And perhaps we want to have no, I think that would work. We can get everything else out of what we've got here. So now we know the program is calling this and then it's calling this. So what we want to do is we want to define what's happening in this program, and the first thing we need to do is to say, right, we want to have, well, we're not really defining this, we're just passing them in. We want to set up the DFO, okay, so let's say, right, so we've got a number of objects which is equals to the weights dot size. We don't even need to do it here, really. We can do it here. and then we want to start to set up our DFO. That's basically just Xcode suggesting to do this. To set it up, well, let's think about this. We need a fitness function. That's the very first thing. So let's set our fitness function. Why are you not showing me? Oh, because it's not a pointer. Set fitness function. Yay, brilliant. Now fitness function takes in a function. We're gonna use a lambda. Okay, so we are gonna capture this because we want to have access to the variables of this class, and we want to follow the syntax that fitness function takes. And to do that, we need to basically pass in a vector, and that's the positions, the dimensions of the flies. Let's just call it P. And voila, we are now ready to define our fitness, which, let's say, at the moment is 0, and we'll have to return it. This is a double, by the way. Right? Double fitness. Let's have a look. Does this compile? No, it doesn't. And the reason why is this. Now, at the moment, each fly will be assessed and return a fitness to 0. What we want to do is to make it specific to our problem. So we're going to have two variables. One is going to have the sum of the weights, and again we start with 0, and one is going to have the sum of the profits, and again we start with 0. And then we're going to have another one, which is going to be basically our do we need anything else? No, we don't. Let's get started. So we want to define our fitness so that taking in the sum of the profits, we want to increase that, but the sum of the weight should not exceed the maximum amount, and we should try and fill our knapsack as much as we can. So one way I thought we could do this is to say, right, so we've got, let's have an error, okay, an error of the weight, let's say. Let's make this equal to this, the absolute value, okay, of a translated to of a -1 translated version of an exponential function. Now, if you know what an exponential function is, you would know that it's basically a function that has this sort of curve. If you picture this line, like here, as the y-axis in a Cartesian graph, and say the x-axis was here somewhere, now the function, the exponential function, would be a curve like this, you know, a bit like a ramp that keeps going up and up and up very quickly after the 0. And what we're going to do by translating down by -1 is that the negative axis is going to look like a bit like a logarithmic slope, and we're going to mirror it back up to the positive axis, whilst the plus is going to basically go the same, just starting from 0. So we're going to have a function that from a certain value will, depending on what you start with, comes down to 0 in a kind of a logarithmic fashion, and then from 0 it goes back up very, very quick, very, very fast. So what we're saying is, if the weight of the knapsack is, if you still got capacity spare, well, then the fitness should go towards the optimum fitness, which is 0, as it approaches 0. And afterwards, if you exceed that, just go berserker and increase the fitness, which is basically negative for us, because the higher the fitness, the less fitness really we have. Our ideal individual has a fitness of 0. Just so that you know what we're talking about. So what we're going to do is that we're going to use the exponential function, and we're going to use any number, let's say 10, and we're going to have the sum of the weights minus the nut capacity, okay, which is the maximum we can get, into an actual knapsack, and then we divide it by the max capacity. Have I got a max capacity? No, I don't I? Oh, no max capacity, sorry, max weight. Why do we do this? Oh, max weight. I don't have a max weight. I didn't calculate. That's okay. Look, basically what I'm saying here is that I want a number. I'm gonna call it max weight, and max weight is basically this for int I equals 0, I less than num objects plus I, max weight plus equals weights I. Okay, and equally I want a max profit, which again is 0, and max profit plus equals no profits I. So these two variables are just gonna help us normalize these variables are just gonna help us normalize the equation. Okay, so to be able to do this, obviously these two guys have to be global to the class, and we can initialize them there if we want. So these two things don't need to be there, and we're done. So now that we've got an error on the weight, we also want to say to increase the penalty if we exceed the nut capacity, just in case we really want to say, look, your fitness should be horrible if you exceed the capacity, because that's definitely a wrong solution. Okay, if we don't get the best profit, it's still wrong, but in a way, like, it could be, you know, an almost good solution. But if you just exceed the weight, then that is the worst thing you can do, because obviously you know, that's the difficulty of the problem, is to find a good value of weight, a good good set of weights, set of objects that give you the maximum profit without exceeding the weight. And we definitely don't want to exceed the weight. So what we've done here is that, say, if the sum of the weights exceed the capacity, then add a lot, and consider that we're normalizing this. So we're normalizing our measures of measurements for fitness. So plus 100 is actually a huge number, basically. long story short, so sum of the profits in this case, and again we normalize with the max profits, and then we say right now fitness is equals to the error on weights plus the error on profits, and we return it, and that's gonna be the fitness of each fly. And then what we want to do is that we want to set up the population side. Okay, set pop size. We want to say, right, let's start with 20 flies, for example, which is a reasonable number. That's the default, so I didn't really have to do that, but just for clarity. And then I need to set the search space width, which is 0 to 1, because an object can either be included or not included in the solution vector, which is which objects do we get into the knapsack, which actually reminds me of something that we haven't defined: the dimensions. So set dimensions. Now that's not what I'm looking for actually. The dimensions are basically setting the solution vector of it that each fly is going to propose, that each agent is going to propose, which will also be the solution vector in the end. And now connecting back to what I was saying, 1 and 0s, is because I want to have a list of objects as big as the number of objects, and this list, this solution vector, is going to be basically a list of instructions that says put it in, don't put it in, don't put it in, don't put it in, and they are as many as the weights. So our solution is going to return which weights in the order given are basically should go into the knapsack to solve the problem. And that's why the search space width should be between 0 and 1. And we also want to set the democracy. And when I say set democracy, I mean set the DFO algorithm that doesn't keep the best in the swarm as a reference, but only keeps the best neighbors for each fly, because this problem is full of local minima, and we want the flies to be able to explore as much as possible our search space to find the best fitness. We want to constrain it because each flies will have a value. It will bear values between the solution of each fly, the coordinates of each solution vector will be between 0 and 1, and we don't want that to exceed 1 or to go minus 0, because it makes no sense and it could create confusion. So we constrain our flies positions, and then finally we set the disturbance threshold, which is basically, if you think in terms of genetic algorithms or things like that, DT is like a random factor that makes the certain solution, certain position, certain values in the solution vector of each fly randomly jump, and this allows us to maybe move a fly to a random position every now and then to make sure that we keep exploring as much as possible the search space. And finally, we run it for a start, just in case we succeed. Obviously nothing happens because we're not running it. Now to run it, we call the run function, which is update swarm, and we should do it for a certain number of times. So we will be for int I equals 0, I less than how many times? Let's put 1,000. Let's put 1,000. Plus I, And once we've run this algorithm, we want to print out what we've achieved. So let's do it before and after. So we're going to say, right, I want to know what the algorithm is doing, and we do it by saying, for example, what is the best fly? What's the solution vector of a fly? So best fly solution, or a attempted solution, and we get the DFO dot get best fly dot toString. Oh, actually this is a vector, so toString. Okay, now bearing in mind that this is going to be numbers between 0 and 1, and if it's above 0.5, it means that we assign it to be in a 1, to be inside the knapsack, and if it's less, we assign it as being outside of the knapsack. Okay, and that makes me reminds me of something. I've totally forgot to in the rush of going through these tutorials, totally forgot one thing. That thing, if it's above 0.5, if it's above 0.5, put it assign it, basically consider it inside or outside the knapsack. Without has to be inside the fitness function. Okay, so let's just close this for a second. Okay, so we've got a line, and let's say, right, so we've got the solution vector coming in, and what we want to do is say, for each p in the solution vector, so for int I equals 0, I less than number of objects, which is also the size of p, so maybe to make it more clear, I could do p dot size, but it's basically the number of objects, so there's no point in wasting computational power. And if p at that I is bigger or equal than 0.5, then we want to say that the sum of the weights increases by the weights at that position. Let's not forget that we're passing in an array, a vector of weights, and they have the same order of the profits, and the succession, the way they go one after the other, their order is the order of the objects, and then the sum of the profits goes up. So by doing this, we're basically saying, every time a fly comes in, see if it check its position vectors, and each value of this vector, which is going to be the same as the number of objects, is going to have a value between 0 and 1, and if it's above or equal to 0.5, then consider that the fly is saying, I'm attempting to put this this weight into the knapsack. I want to see if this solution works, or this weight outside, so then I don't take neither weights, neither profits. And ideally, we want to choose always the best fly, and make the others try to fly towards the best fly, and find the best area in the problem. Like if the problem was an actual n-dimensional search space, and these flies were flying across it trying to find a solution, which is the right combination of weights. So then what we want to print out at the end, to maybe we want to know which fly. So the best fly is fly number something, and we're going to get dfo dot what are we gonna do? We're gonna do dfo dot get best fly dot get, what are we gonna do? We're gonna do get, you know what, actually I think there is a get best fly index. Yeah, there is. Good. So we've got fly, and we might want to know we've got the solution, we've got that it's proposing, we've got its index, and let's get the fitness. Okay, so there we go. dfo dot get best fly get fitness, and there we go. Now actually, to make it more clear, what I'm gonna do is I'm not gonna get this string, okay? I'm gonna get the I'm gonna get the what can I get? The vector, the actual vector, right? So I wanna get the best fly get fitness. No, I want what do I want? Get position. Yes, and I'm not gonna print this out because this is a vector. What I'm gonna do is I'm going to create a new vector. Okay, standard vector, and it's gonna be a vector of doubles because we want to have the same as the position, the solution vector of the fly, and let's call it best pose interpreted, and I'm going to say this is going to be equals to this, and then for int I equals 0, I less than number of objects, because that's the same as the dimensions, I plus plus, and we are going to say if the best position interpreted is equal to actually is less than 0.5, then best position interpreted I is equal to 0, like that. Otherwise, the best position interpreted at that I is equal to 1. And there we go. So now we're going to print this instead. We're going to basically do a is there a best position interpreted? Is there a toString? No, there isn't, isn't it? I'll tell you what. I think I have some utilities in the. Let me have a look. I think I put into DFO something. Let's have a look at DFO. Yeah, helper. Right. So this helper should have a method. What's it called? Oh, DFO helpers, right. So the FO helpers, I should have a method that allows you to turn a string, a vector, into a string. Yes, bang. So we print this before and after. Okay, so we see what the best fly when we generate random flies is, and then we update the algorithm 1,000 times, and then we get a solution. Okay, so then we check at the end. Let's get ready. See if we oh if we let's have a look how we are doing. Blitz succeed. Oh, bad access. What am I doing? No, I don't know. Ouch. Why? What am I doing wrong? I'm setting the fitness function. Oh, of course. I'm not generating the swarm. Sorry, bear with me. I need to generate a swarm, and we just want it on the positive axis, because if you do generate swarm, it interprets that the width, when we set it to 1, should be mirrored both to the plus and the minus. So it could be, between -1 and 1. By doing generate swarm positive axis, you basically just initialize the flies between 0 and 1, and then later on you constrain them between 0 and 1. So these two are kind of working the same way to define the problem as we need to be. And now we try again. Ooh, what's happening? Bad access. Right. Right, oh, of course, yes. Now I see. That is me being an idiot. So when I set the disturbance threshold, I was actually setting the dimensions. So I was basically having dimensions of less than 1. So there were no flies in this swarm at that point. Alright, right. Okay. So now we've got something that works. Can get rid of this. That was just a check-in. So look, let's have a look at what we've done here. We start with with all flies at random, and it says this is the best solution. It's 1 0 1 1 1 1 1 0 0 0 1 0. Sorry, all zeros. And then after 1,000 rounds, we are saying, right, actually this is a better solution. If we run it again with more attempts, we go back to that. So we start to be confident, and actually this could be the best possible solution. Now I want to just play around with the fitness function here and just have a look. Now we got a slightly different result now, and I wouldn't want it to be because of some issues with the fitness function. So I just want to play along with it, and 1 1 1 1 1, and let's just keep basically changing around our one sec. No, that's fine. So actually this starts to seem like a good endpoint for our attempts. We've got now 10,000 flies. We're getting there quite quickly, so we can even increase that to 20,000. See if that changes. It seems like that's sort of a good solution. Let's reduce that to 10, because we don't want to give too much importance to the profits. Otherwise, there's no point in doing this. Okay, so we'll stick to something that we know can work, and on a solution that I've already worked on. But this is behind the scene. What is this? This is exactly the same stuff, and you find it, the full source code inside of the problem. And what we're gonna do is we're gonna test what the solution should look like. So this is already something that I've done before. I know it works. I checked it with the website, and this is what we should get: 1 1 1 1 1 0 1 0 0 0 0. What are we getting here? 1 1 1 1 0 1 0 0 0 0. That works. We've just checked it. We've got a working DFO that is going to basically show us how to fit weights into our knapsack so that we maximize the profit and we keep within the constraint of our bag. And now, challenge. First of all, let's bring up my face. So the challenge now is, can we do this with multiple backpacks and set of weights which keep increasing and increasing and increasing and increasing and increasing? Well, the challenge is open, and let's see if I can find solutions, or if you can find solutions. It's much tougher problem if you have multiple backpacks, but you never know. Let's see if we can use some intelligence next time, artificial intelligence next time to solve this. And if you are watching this and are thinking, oh, I might want to try out the solution, you've already got here a version of the algorithm that works for the simple one backpack problem. Well, then just what if we have two? How would we set it up? How would we create the fitness function and so forth? How are we going to do this? Let's see if anyone is willing to take this challenge. Anyway, for today, I think that's it. See you next time. Ciao.